Okay, so time to start. This week the topic is on probability. So the reason is, number one, it is very closely related to the topic last week, which is about counting. And then in future we are going to sometimes we mention probability in, for example, in game theory or in other topics. So that's why we have to learn a little bit about probability. So the plan for today is, okay, so we give some introductions and see the connection between counting and the calculation of probability. And then we'll see several examples. And then we'll talk about the meaning of independent events and introduce conditional probabilities. Okay, so let's try. Let me ask two questions, and then hopefully by the end of the lecture, you'll see the answers. Okay, so these questions are typical, well-known. So the first one is so-called the birthday problem. Okay, so the setup is this. Suppose someone offers you the following bet. Okay, you can put $10 or whatever. So there are two persons in this LT right now with the same birthday. So the question is, would you bet for or against this? But with this attendance rate, probably the answer is obvious. But right, okay. So, but maybe there's, after a few minutes, some people will come in, and then you'll see. Okay, so we'll see that. Well, this involves probability, and so the goal of probability is to model so-called uncertain situations, right? And to quantify the uncertainties. So sometimes we cannot, unlike in logic, we have this very, very affirmative answer to everything, either true or false. But in the real world, sometimes we cannot have complete information, or so we have to take chances, right? So in many situations, probability probably is more useful than some mathematical theory. Okay, so that's the introduction. Now there's another well-known example. So it's like you are going to a party, and then some people will challenge you or whatever. So this is well-known. So probably most of you have heard of this. So here is okay, so I'll show you the setup. So it's called a multi-hole game. So you are in a game show. So there are three doors here. So the doors now are open, but it will be closed, right? So there are three doors, and you are asked to guess the door behind which is the Ferrari, right? So behind the door there are two goats, or two something we don't like, right? But there are something we like. I don't know. So maybe some of you like. So there's a car here, right? So there are three doors here. So you are asked to guess which door, behind which there's a car, right? So you try your luck. You point at some of the door. And then after you pick one of the doors, the show host, who knows where the prize is, because for example, you choose this one. Now, one of these doors, there's a goat inside, right? So the host knows where it is. So, the host knows where the car is, right? So he'll open the one which does not have the car. Okay, suppose you choose the first one. In this picture, he is going to open this one. Okay, and then he asks you whether you want to swap. You want to change your mind instead of stick with this one you choose. You want to swap. You want to change to the other one which is closed now. Okay, is it clear? Or you have heard of this, right? So the question for you is, should you switch your choice? You see what I'm saying, right? Okay, so you choose one, then the host open one with a goat. That asks you, do you want to change your mind, right? So the challenge for you is, do you want to change, switch, or not switch? Okay. Now it seems all random, right? It seems like it's equal chance, but we'll see whether it's really equal chance or not. How many of you have heard of this? This is well known. Okay, 1, 2. Okay, so less than. Okay, less than I expected. Okay, then you think of it. what should you do? Okay, now how many people in the? Okay, still okay. Probably the question 1 is not ready. Okay. So now let's talk about, let's go from the counting to probability. Okay. So last week we talked about the counting, right? So we talked about the game of poker, and we have calculated all possible 5-card hands, right? So the total number is this number, and then we calculate certain things like this royal flush, right? How many ways you can get royal flush, right? So well, there's a fancy name for the set of all possibilities. So it's called a sample space. So the set S, which is defined by all possible 5-card hands, is very often people refer it as sample space. Okay, so we have done our counting. So we count royal flush. There are only 4 possibilities, and then 4 of a kind. The number of ways is much larger. So it's 624. So if you look at the chance, right? So the chance to get royal flush will be 4 over the total number, which is this percent. It's extremely slim. Right? Now, 4 of a kind is much better than this, but it's still quite small, right? It's 0.02%. So it's really, really small. But down the road, if you calculate those more popular hands, then you'll get better chance. Right? Okay, so the number and the probability or the chance you get these numbers explains why the casino run things in that way, right? So they know they're really good at calculation. Okay, so now let's introduce some jargons, right, or some terminologies. So experiment. So an experiment is a situation whose result or outcome depends on chance. Right? So for example, we'll call these kind of things experiments, unlike experiment in physics or in biology. So we'll say these kind of things are experiments. So tossing a coin, so that's experiment. So the outcomes, so there are 2 possible outcomes, head or tail. H stands for head, T stands for tail. And there is a depend on chance, right? So you don't know. I don't think you have the skill to always get head. Right? So this is, we call this kind of thing an experiment. Okay. And then throw a dice. Here, I think people now use dice as singular also. Usually dice means plural, but I guess now people are, the language skills are going down. So anyway, so this is maybe it's a mistake a few years ago, but now probably it's not a mistake. Okay, anyway, so you throw a die. Throw a dice. There are 6 possible outcomes. You know that there's a cube. You have a small cube, and then it's 1, 2, 3, 4, 5, 6. Right? You toss it, then you can see the points, or you can see the number. Okay. So the outcomes are from 1 until 6. 6 outcomes. Or you can pick a card from a deck. So there are 52 possibilities. So we are familiar with this in the poker example. You can also toss a coin several times. Right? For example, if you toss it twice, now there are 4 possibilities. Right? So it's head, 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 tail. First one is tail, second one is head, and then both are tail. So there are 4 combinations. Right? So if you toss a coin at 100 times, then you'll get 2 to the 100 many possibilities. Right? Okay. So now let's define sample space. Right? We already know the sample space. The informal idea is all possibilities. So it's called sample space. Okay, so let's try. So the set of all possible outcomes of an experiment is called the sample space associated with this experiment. Okay. So the element in the sample space is an outcome. Right? So for example, in the previous slides, in the experiment of tossing a coin, the sample space has two elements, head and tail, right? And you know what the others. So if you throw a die, you'll get 6 possibilities. So the sample space consists of the numbers from 1 to 6. And then if you pick a card from the deck, you'll have 52 possibilities depending on which card you draw. Right? So, and then tossing a coin twice, you have these. I just said it verbally. Okay, so it's quite easy to understand. Now, the word event. Okay, so we are going to use these words quite often in the later part of the lecture. Okay, so an event associated with an experiment is a subset of the sample space. For example, in the experiment of throwing a coin twice, right? So the sample space consists of these 4 elements. So now what is an example of event? So the event of getting the same result twice, right? So this is given by the subset of, okay, the same result. It can only be head, head, or tail, tail, right? So the event is a subset of the sample space. Now we code them event, okay? Let's see something similar. So in the experiment of throwing a die twice, so the size of the sample space is 6 times 6, so it's 36. So the event of getting the same number twice, right? Getting the same number is given by the subset. Okay, so you either get double 1 or double 2 and all the way to double 6, right? So there are 6 elements. So this is another example event, right? So it's just something happens. Okay, so and there are some other words. It's extremely intuitive. The names will suggest the meaning. Okay, equally likely. Okay, if each outcome of an experiment has as much chance of occurring as any other, then we call them equally likely. Okay, so this is kind of sort of fairness, right? So if you toss a coin, if the coin is not biased, and then usually you have equal chance of head and tail. If you throw a die, you have equal chance for each number, right? So this is called equally likely. Okay. For example, if you toss a 5 coin, a head or a tail is equally likely, right? So well, we are going to use the word probability in a second. So actually, it says the probability of head happening is the same as the probability of the event you get tail. Both of them are 1 half, right? Now, in the other example, if it's equally likely, then there are 6 numbers. So the probability you get each number is 1 over 6. Right? So because they are all equal. Okay. Now these are extremely easy. Okay. So now we can describe this is the main idea, main concept of today. So let A be an event in a sample space S. Well, in other words, A is just a subset of S. So the probability of event A is calculated in this way. So the P of A stands for probability of A. Is equal to the size of A, the number of elements in A divided by the size of the total size of the sample space. So among the total possibilities, how many how often A happens. Right? Here, because we are in a general education module, we don't we assume we are working on a finite sample space. Right? If you are in statistics department, you are going to study these other like continuous, and so you have lots of more complicated situations. But well, let's just talk about finite sample space. Okay, so therefore, now we already go from counting to probability, right? So the computing the probability actually is more or less, the challenge actually is counting, right? So if you know how to count various sets, then you know how to calculate various the probability of various events. Okay, so. As I said before, we only consider finite sample space because we don't want to talk about integrals and so on and so forth. Okay. All right, so so simple example. Suppose we toss a coin 3 times. So the sample space there are 8 elements, right? So now suppose you look at this event, you always get the same result. So either you get 3 consecutive head or 3 consecutive tail. So the probability of this event is just the number of elements in this set, which is 2, divided by the total possibility, which is 8. So this is 1/4, right? So this is, again, extremely simple. Okay, so so let's see some examples of calculating probability. These are, again, fairly simple, but let's make sure we understand simple things. Okay. So if you toss a coin 6 times in a row, what is the probability that you get more head than tail? Okay, so you toss the coin 6 times, and then maybe sometimes you get 2 heads and 4 tails. Sometimes you get all heads. So the task is to calculate what is the probability that you get more H than T, more heads than tail. Okay, so you have to figure out what is sample space, what is the event, right? So as a set, what the event is. Okay, so the sample space S, you can identify this as a string of length 6 consists of either H or T, right? So there are 2 to the 6, which is 64 possibilities, because the first toss you have 2 possibilities, second toss another 2 possibilities, so it's 2 times 2, and so there you have 6 copies, so it's 2 to the power of 6. Okay, so now let A be the event of this, right? So we have to have more head than tail. Okay, so then as a subset of S, A is the disjoint union of the following subsets. Okay, so what are the configuration or the possibility where you have more head, right? So the first possibility is you have exactly 4 heads, and then you have two tails. So you get more heads than tails, right? So in this case, what is the number? So it's 6 truthful. Because you have 4 heads, you're just 6 truthful, right? Okay, and the other subset, so we want to decompose A into 3 disjoint subsets. The first one is you have exactly 4 heads. The second one is you get exactly 5 heads. And the last one is you get 6 heads, right? So these are the situation when you get more H than T. Okay. So now let's do the calculation again. So the outcome is 5 heads. The number of ways is 6 choose 5. And then the third one is just one possibility. Everything is H. Okay, so the size of A is 22. If you add them, you get 22. So the probability of A is 22 over the size of the sample space, which is 64, so you get this number. Okay. Now, actually, in this calculation, we have used some counting principles. So, for example, we implicitly use this so-called addition principle. It says this. If A and B are disjoint subsets of S, we also say that A and B are mutually exclusive events. Right? For example, in this example, 1, 2, 3 are mutually exclusive. Right? If this event you have 4 heads, you cannot have 5. Right? It's mutually exclusive. Okay. So then the probability of A union B, of the disjoint union, actually is the sum of probability of A plus probability of B. So the reason is because we have this, right? So this is the size of the union, which is equal to the size of A plus size of B, because there is no intersection, because they are disjoint, right? And then the probability of A union B is just the size of A union B divided by the size of S. So you know this, okay? So this is easy. And then by the same calculation, you can transfer our principle of inclusion and exclusion to probability, right? So it's always, people shorthand it as pi, P-I-E, okay? So, so using the language of probability, it says if A and B are events, then the probability of A union B is equal to the probability of A plus probability of B minus the probability of this event where A and B happen, both happen. Okay. Again, the proof is just like this. Okay, we also, very often we also use this. So suppose, remember we use A to the power of C denote the complement of A, the element not in A. Okay. So in this case, the universal set or the universe is just the whole sample space, is S, right? So if A complement is the complement of A in S, and then the probability of A complement is just just 1 minus probability of A, right? So in other words, if you add A happens and you add A does not happen, you get 1, right? So it's either A happen or it does not happen. So it always add up to 1. Or you can, right, so it's the same. You can say the probability of A does not happen is 1 minus the probability A happens, okay? Right, so. Okay, so now let's maybe there are 3 more examples. Okay, so let's look at some examples. So example 2, which is this question 1. Okay, so we have a glass jar contains 1 red, 3 green, 2 blue, and 4 yellow marbles. Okay, so if a single marble is chosen at random from the jar, right? So the word at random means this, means each such, not integer, such marble is equally likely to be chosen. Sorry, there's a typo. So what is the probability that it is yellow or green? Right, is it clear? So we have a jar of marbles, and then there are 10 marbles. So now, what is the probability you get a yellow or a green? Okay. So, well, the answer is quite easy, right? The probability of getting yellow or green by this, because this is destroying events, mutually exclusive events. So it's just a probability of yellow plus probability of green. So this is how many yellows? We have 4 yellows, so it's 4 over the total number of marble. It's 4 over 10 plus 3 over 10, so 3 is the number of green marbles. Okay. So you get 7 over 10. Okay. Now, this is slightly more complicated. So a single card is chosen at random, the same meaning, equally likely. Okay. From a standard deck of 52 cards, what is the probability of choosing a king or a club? Okay. So the answer is, again, using this PIE, right, the pi. So the probability of getting a king or a club is equal to the probability of getting a king plus probability of getting a club minus the intersection. The intersection is you just get the club king, right? So which is, okay, so you get 4, you have 4 kings and 13 cards in the suit of club. So the sum is this, and take away 1 overlap, which is the club king, right? So you get this number, okay? Now, this is almost like the same example in counting. So an integer between 1 and 100 inclusive is chosen at random, meaning equally likely. Okay, just pick them. Find the probability that it is a multiple of 2 or 3 or 5. Right? So this is just parallel to the counting. Okay, so let's go through them really quick. So the sample space are all possibilities, which are the 100 numbers, right? Now, let's use A, B, C to denote the events, right? Let A, B, C be the events that the chosen integer is a multiple of 2. This is for A. B is the integer is multiple of 3, and C is the integer is multiple of 5. Okay? So when we count the number of multiples k, we have used this notation x sub k, right? So let's recycle this. Let x sub k denote the set of integers in S, which is a multiple of k. For example, x sub 2 is the set of all even numbers, multiple of 2, okay, and so on. Okay, so then you know how to calculate this, right? So you calculate all these relevant data, and then you calculate the probability, which is for example, the first one, you divide by the size of the sample space, which is 100, right? 100 is very easy to divide, right? So if you divide, you get this 0.5 and so on and so forth. So you get all the relevant data in terms of probability, and then you use this inclusion-exclusion principle. You get the probability of the union, which is either this or that, is equal to, okay, it's too long, right? So you add all the singletons minus the pairs and plus the intersection of 3. So in the end, you get this number. Okay? Okay, now good. So now let's see how many people do we have. Good, we have a chance. Okay, so for those who came in late, the first slides I showed is this question. So in a group of n people, n is the number of people in this LT. What is the probability of there are 2 persons with the same birthday? Okay, so let's answer this question and then apply to the side, right? So it is, so two person with the same birthday, the probability is 1 minus the complement. The complement means no two person have the same, they all have distinct birthdays, right? So it's, the probability is 1 minus the probability of n persons all having different birthdays, right? So you are with me up to this one, right? So what is the sample? So the sample space are of size 365 to the power of n, right? Because you have n person, each person could be one of the 300. Okay, let's forget about the leap years. So let's just, right? So each person could born one of these 365 days. So you have n person, so the sample space has size this number. Okay. Now let A be the event that these n persons have different birthdays, all have distinct birthdays. Okay, so this is the A. Now I claim the size of A is this. Is this right? So for the first person, he can, okay, so let's, he'll, it's like he pick his birthday, right? Something like that. So his birthday is day, I don't know, K1 or something. And then after he fixed his birthday, the second person, because it has a different birthday, so he can only choose the remaining 364 days, right? As if he chooses, right? So now let's settle two person, right? So then look at third person. Now there are one less chance, right? So all the way to n. So you have these possibilities, okay? So the result is the size of A is 365 factorial divided by 365 minus n factorial. Okay? So this is the size of A. This is the size of sample space. Okay? We want to find 1 minus the probability of, okay, so the probability of two persons have the same birthday is the probability of the complement of A, right? So it's 1 minus this number. Okay? Now you have calculators, so when n equals 23, the probability is this. Please verify. I tried this, right? So it's indeed, it seems like this. So do we have 23? So we have now, if we have 23 people, then it's about half-half. But if we have 30 people, and then the probability seems much larger. Now, if we have 50, I guess I'll never see 50 people unless it's a midterm test. Right? So then we'll have a much bigger chance. So maybe during the break we can try. Maybe, do we have 30 people? Probably have 30 people. So anyway, so this is a. So if we have 30 people, you would bet that there are two persons, right, which have the same birthday. Okay, so is this all right? Okay. Now let's continue. So the next topic is about whether two events are independent or dependent. Okay. So suppose you toss a fire coin twice. Would you expect the outcome of the first toss to influence the outcome of the second toss? The answer probably no, because they are not related, right? You toss one after you finish tossing, there's nothing, there's no relation between the first one and second one, right? Okay, so this leads actually to a very general and important concept called independence. So the mathematical definition of independence is not describing the events. Instead, it is defined by using probability. Okay, so the mathematical definition goes like this. So let A and B be two events. We say that A and B are independent events if the probability of both of them happens, A intersect B, right? So the probability of A intersect B is the product of probability of A and probability of B. If this happens, we call it independent. Right? So we don't try to describe what events are independent, but we use probability. Okay. So let's, before we look at example, there are maybe in future we are going to see 3 events are independent. Maybe not. Maybe in this class we will only see 2 events are independent. But anyway, in case we are going to, we will see 3 events are independent. The criteria are slightly more complicated. Right? So we say that events A, B, C are independent if they are pairwise independent, and that's not enough. You have to try the 3. Okay, so we say the 3 events A, B, C are independent if A and B are independent, A and C are independent, B and C are independent, and we have this, the last equation, P of A intersect B intersect C is the product of PA times PB times PC. Okay. So, well, if we know what is independent, we certainly know what is dependent, right? So the events that are not independent will be called dependent. Okay. This is very natural. Okay, so look at examples, right? So how do we tell 2 events are dependent or independent? Let's look at example. So this example says, the first example says this. The scenario is, so the experiment is we toss a fire coin twice. Okay. So event A says, so A be the event of getting a head at the first toss. Okay, we toss it twice, right? So A says the first toss you get head. Okay. And B is the event of getting a tail at the second toss. Okay, so I don't care what the first toss is, what the result is, but the second one I insist is a tail. Okay, so now the question, so the conclusion is, so A and B actually turns out to be independent. So, well, we verify this by using our definition. We check the probability, right? Okay, so the sample space, we have seen it many times. There are 4 elements here. And the event A, which is the first toss, is a head. So you have H, right? The first one must be H. So you have 2 possibilities because you don't care about the second toss. Right? So A has, the event A is this subset. Similarly, event B is this subset. You get a tail at the second toss. Okay. Now, the intersection of them, A intersect B, well, there's only one common element, which is HT right here. Okay? So now let's check the probability. If the probability satisfies the equation, then they are independent. Otherwise, they are not independent. Okay? So what is the probability of A? Okay, so it's half. What is probability of B? Okay, half. What is probability of intersection? 1/4, right? Okay, so PA times PB happens to equal the probability of the intersection. So that verifies they are independent. Okay? Okay, so let's try another example. Let's see dependent events. Right? So, so the same scenario. The experiment is we toss a fire coin twice. Okay, so let C be the event of getting at least 1 head. Maybe toss twice. One of them is head. Okay. The D be the event of getting at least 1 tail. You toss them twice, at least one is tail. So the question for you is, are C and D independent events? Right? Okay, so again, we use definition. We check the mass. We check the probability. Okay? So the same sample space, because we toss it twice, same sample space. Now this time, the event C is getting at least one H. Well, so you get the first three. I don't know why I changed the order. Okay, so these are this subset represent the event C. Okay. So the probability is 3/4, right? 3 divided by 4. Okay. Now D is getting at least one tail. So one of them is T. So you get these. So the probability of D is the same, 3/4. Now what is C intersect D? So if you look at the common elements, the first two are common elements. So C intersect D has two elements, the head, tail, tail, head. Okay. So the probability of the intersection is half. Okay. Now let's verify. So is the intersection, the probability of intersection, equal to the product of the probability? No, because this is 1/2, but if you multiply this, you get 9/16. So it's not equal, right? So therefore, C and D are not independent. Well, it's just dependent. Right? C and D are dependent. Okay? Now, okay. So let's look at several other examples. These examples will lead us to the binomial distribution. But anyway, so let's look at some other examples. Okay. So here, so this example have several parts. Okay. So it says a loaded coin. Loaded coin is a biased coin. So the fire coin is a coin which are make head and tail equally likely. The loaded coin is not. It's maybe on one side is very heavy, and so there's more chance to show one side. Okay, so a loaded coin is tossed 5 times. Okay, so assume that the probability of a head is, okay, instead of 50/50, the head has more probability. So the probability of head is 0.6. 60% you get head. Right? It's loaded coin. Okay. And assume the tosses are independent of one another. So find the probability of obtaining, okay, all tails, or at least one head, or exactly one head, or exactly 2 heads. So we are calculating several events, the probability of the events, right? Okay, so, well, this essentially we do the counting, and so if the probability of getting a head is 0.6, then the probability of getting a tail is just 1 minus this, right? Is 0.4. Okay? So now look at part A. So we want to calculate the probability of all tails, right? So the probability of all tails, which is probability of, okay, so it's like this event. So it turns out to be, here we use the independence, so you get the product of these, right? So you get 0 to the 4 to the power of 5, because the probability of tail, P of t, is 0.4. You have 5 of them. So you get this. This is the probability of getting all tails. Okay, now how about the part B? Says the event that there is at least one head. So this is just the complement of all tails, right? So if it is not all tails, it means it has at least one head. So the probability of at least one head is 1 minus the probability of all tails. So we calculate all tails, so we get this. Okay. So now C and D leads us to the more general case. Okay, so let's look at C. So so part C asks us to calculate the probability of the event exactly one head. Okay. So now let's just spill it out, right? So what are the possibility of one head? So there are these 5 cases, right? So it's a probability of this happen. This event stays 4. The first toss you get head, the rest are tails, right? The second item here says the exactly one head happens at the second toss, right? Then it's at third one, is fourth one, last one. So these are disjoint events, so you can calculate the probability by getting these. Okay. So now what is the probability of the first one, for example? Okay, so this is the probability of H happens, which is 0.6 with this probability. And then we have to multiply the second, which is the probability of T happens. That is 0.4. But we have 4 copies of T. So that explains you have a power of 4 here, right? So this is a probability of the first item here. But the rest are the same because the calculation will all give you this number. So altogether we have 5 sum n, right? So we just multiply 5 to this number. It turns out to be this. Okay. Is this clear? Okay. You have a question? I'm sorry, you're asking? We'll hit that. Okay, so C and D are actually a special case of what you just asked. Okay, so what is part D? Part D says, how about the probability of exactly 2 heads? Well, you list out all the possible cases where 2 heads happens, right? For example, the 2 heads can happen at first 2, or maybe like this, or maybe happen last 2. So there's lots of other cases in between. But the total number of cases is you choose, among the 5 tosses, you choose 2 positions, right? So this is 5 choose 2, right? So multiply. Now you have 2H. I don't care where the H showed up, but 2H, the probability will be 0.6 to the power of 2. Right? Now the remaining 3 letters, 3 tosses, we get tail. So the probability of getting tail is 0.4, so you raise it power to the power 3. Right? So the total number is this. Okay? Right? So now we can answer your question. So your question is, how about n tosses? We look at k, exactly k heads. Right? So this is the pattern. Okay. So in general, let's look at this. So it has a fancy name called a binomial distribution. So I will not define distribution, but it has a name. This kind of thing has a name. Okay, so the example, the scenario is this. Suppose a coin is tossed n times, right? This is exactly what you asked. And suppose the probability of a head in each toss is p. Just now, the p is 0.6. In general, we just know it's a number between 0 and 1. So it's just p, right? So assume that the tosses are independent of one another, and then the probability that there will be exactly k heads. In other words, well, there's a fancy description called x equal k. Well, forget. The x is not important. Okay. So we want to calculate the probability of exactly k heads. Okay, so the probability is calculated in this way. Somehow people use x equal k to denote this event. The reason is in this paragraph. I will explain in a second. Okay, so the probability is n choose k, and p to the power of k times 1 minus p to the power of n minus k. You can see just now the example 3D is like this, right? So you have n choose k times p to the power of k, and the 1 minus p to the power of n minus k. Right? It's the same. Okay, so let's just repeat the reasoning. So the sample space has size 2 to the n because you have n tosses. Each time you have 2 possibilities. So you have sample size 2 to the n. Now, there are n choose k many elements in S which with exactly k heads, right? Because it can happen at any k positions. So it's n choose k. Okay. So the probability of obtaining and the probability of obtaining each one is because you need k heads and exactly n minus k many tails. For that to happen, because to get head, the probability is p. Now you need to make this thing happen k times. So therefore, it's p to the power of k. Now for the remaining part, you get 1 minus p, which is the probability of getting a tail, right? So this is 1 minus p times the remaining number. Okay, so it's to the power of n minus k, but you have n choose k many possibilities, so you have to multiply this n choose k. Now, in probability or in statistics, people have this, there's a jargon called a random variable, which is a function from sample space to somewhere. So in this case, x will, in this particular case, x is, okay, people always call it a random variable, which takes a value of number of heads. So by writing x equal k means the random variable take value k. It has exactly k heads. So we are trying to calculate this probability. Okay. If we really hate random variable, you can write this in words. So let a sub k be the event of exactly k heads, and then you calculate p of a sub k. It's the same. Right? But for those who has experience in probability, this is very common use. The p of random variable equal to something. This is it becomes standard. Okay. All right. So. Okay, so let's finish this example, then we take a break. Okay, so here, suppose you have a monkey. Then this monkey somehow likes typing, so he types at random on a typewriter. Well, I guess nowadays there's no typewriter anymore, just jumping up and down the keyboard, right? So, okay. So, and produce a sequence of 1 million alphabetical letters. Okay, so just a sequence without space. Okay. So now we divide this sequence into blocks of 6 letters, while ignore the remaining few letters. Okay. Assuming that letters are produced independently of one another, in other words, they are equally likely, right? And each letter is equally probable to be typed out. We want to find the probability that one of these blocks is a sequence genus. So the monkey jumping up and down produce a very, very long string, and then we cut string into 6 letter words, right? So now what is the probability of this particular word, genus, showed up? Okay? So that's our question. Okay, so now here's a calculation, right? I hope this is, I took it from the book, so I hope this is right. So there are these many words, right? So a block of letter is 6-letter words, right? So there are, you have 10 to the 6 divided by 6 many words, block of letters. Now, the probability of a block is the word we want is P, where P is 1 over 26 to the power of 6, right? Because you get the first position, you have 1 out of 26 chance to get G, get this particular letter, right? And same for the other 5. So altogether, you have 1 over 26 to the power of 6. Okay? Now, it's easy to calculate the complement. So the probability that none of these block is genius is so it's 1 minus p to this power. Right? So the first block is not genius. The probability is 1 minus p. The second, again, 1 minus p. The third, 1 minus p. Right? So the genius, the word never showed up, means all blocks do not have genius. Right? So it's a product of all these. So you get, this is 1 minus is there something wrong? So I guess you substitute here. I don't know. So you substitute p by this, okay. And then raise the power. So I guess maybe here is something wrong. Yeah. Okay, I'll check. Yeah. And then the calculation goes like this. You can help me to check it. Okay, so the probability that one of these blocks is the word is like this. So because we just calculate none of them is genius, is this probability. So the probability is this. Okay, so let's take a break, and if you want, we can check the birthdays and see whether there's. Do we have 30 people? Good, we have more than 30 people. So there's more than 70% chance we will have 2 persons have same birthday. So should I pass you a piece of paper and just write your birthday? Okay, so let's do it. Right? If you don't want to write, then you can skip. Let's continue with the lecture, and while the paper was circulating. Right? Okay, so now we want to introduce a new concept called conditional probability. So sometimes the events are dependent or not. So we may have this situation. So let A, B be events in a given sample space S. So the conditional probability of A, given that B has occurred, is denoted by this symbol, P of A with a vertical stroke, conditional B, is defined to be the conditional probability is the probability of A intersect B divided by probability of B. So why do we have this funny expression? So this is actually, we shrink the sample space from S to B, right? So we are saying under the condition B happens. So we ignore all the other events where B doesn't happen. So we look at, if you draw the Venn diagram, we are looking at the we all focus on the set B. Everything happens inside B, right? So inside B, you want to see what is the portion where you can see A, right? So it's A intersect B. So this will give you the relative probability, or people call it conditional probability, okay? So, so let's test our understanding, okay? So the definition of conditional probability is like this, right? So now let's see, is this true? Suppose A and B are independent. Is PA equal to P of this conditional probability while assuming B happens, under the condition B happens, A happens, right? So, and also the claim is it is equal to the conditional probability of this. Is this true? Yes, right. People say, of course, right? Okay, so why of course? So I'm slow. So let's show the first equality. So look at P of this conditional probability. It defined as this, right? So the middle term is just like this. Now, P of the intersection, now we have to use they are independent. So if they are independent, the intersection will be the product is PA times PB, right? Now you cancel off PB, you get just PA, right? So the same thing for this is just a symmetric, just change A to B. So, so the argument is just like this. Okay. Now let's look at some examples. So the example of conditional probability, suppose two fire dice are tossed, right? Find the conditional probability of getting a double, means you get same number, given that the total score exceeds 10. So this is conditional probability, right? So the condition is the total score is bigger than 10, right? Now you want to see if we focus on the subset, what is the chance to get a double? So this is a conditional probability. So the solution is we just use definition, right? So let A be the event of getting a double, B be the event that the total score exceeds 10, and then we can actually write down what is A, what is B, right? So A will be these six numbers, six elements, right? 1, 1, 2, 2, you get same number, right? Now B, to get the total number bigger than 10, there's only 3 possibilities, right? Because if you have 4 plus 6, it's just 10. It's not bigger than 10. It doesn't exceed, okay? So now the conditional probability is, by definition, is the probability of the intersection divided by probability of B. So the intersection, there's only 1, 6, 6. So the intersection, the probability of the intersection is 1 over 36. Now the probability of B is, there are 3 elements, so you get 3 over 36. So you get 1/3. Okay? Now there's another example. Let's see. So suppose Mr. 10 has, there's a typo. Okay, 3 children. And you know that he has at least 1 son. Now, what is the probability that his first child is a son? Okay. Right? So let's assume that equally, you can get son or daughter equally likely. Okay. So the solution, again, we follow the definition, right? So the sample space is, there are 8 elements, right? Whether Mr. Tan has 3 sons or 3 daughters and any possible mix. So let A be the event of first child is a son. B be the event of at least 1 son. At least 1 child is a son. Right? So then the conditional probability, again, we use the formula. So is the intersection. Intersection means the first one is a son and at least 1 son. So actually it's is all of them, right? So there are 4 possibilities. Now B at least one son, so exclude O daughter, there are 7 possibilities, right? So you get this probability B is 7 out of 8, right? So you get 4 over 7. Okay, now very often when we compute the probability, very often the drawing a tree will help. I changed the slides a little bit because in the earlier slides there's something misleading. Okay, so let me say the message. Right? The message was, when computing probability involves a sequence of experiments, we can use a probability tree, something like this, to help us, right, to keep track of the outcomes. So the rule is the probability of arriving at a destination, which is some leaves here, right, a destination, is a product of the probability along the path. So for example here, so tossing a coin 3 times with a probability of head equal to P. So this is a biased coin. So tossing the first coin, there are probability P, with probability P you get head, right? The second toss, again with probability P you get head, and so on and so forth, right? So now you want to calculate, for example, what is the probability I get head, tail, head? So the probability of getting head, tail, head, that is the probability of arriving at a destination. The destination is here. Okay, so is a product of the probabilities along the path. So it's P times Q times P. So it's P squared Q. Okay, so this is the so-called probability tree, and it is quite helpful, you'll see, for our computation. So for example, this is a simple example of using probability tree. So we toss 2 dice. If a double is tossed, we do one thing. We throw 2 fire coins, right? Suppose we don't get a double, we will toss just one coin. So find the probability of getting no heads. So this is example of, okay, we have a sequence of 2 events, right? The first one is tossing 2 dice. The second event, well, it depends on the first event. So the second event is, okay, if it's a double, you do this. If it's not, then you do that. And then each of them has their own probability, right? So now we want to find a probability of some events here. We want to find a probability of reaching certain destination, okay? So the solution is the probability of what do you want? Getting no heads, right? No heads is equal to, now look at the outcome here. No heads, this destination has no heads. The other destination have no head, right? So to reach this destination, the probability is the product of the probability on the edges. So to get this destination, we have to, the probability is 1 over 6 times 1 over 4. So that gives me this. Okay. Now to get this destination, by the rule of the tree, I have to multiply this probability and that probability. So it's 5 over 6 times 1/2. So the probability of no heads is this. Okay. So this will help us to calculate probability. Now let's try one more. Okay. So this is some clinic and okay, smokers, whatever. So suppose that probability that a smoker has a respiratory problem is 0.7, while the non-smoker has this. Okay, so it's the 1 minus. Wait. All right. No. Okay. The non-smoker. Okay. Sorry. the smoker get the problem is this probability. The non-smoker, smoker have problem is this probability. Non-smoker has problem is that probability. Okay, sorry, yeah. Right, and then what is the probability of a smoker, non-smoker? So 20% of patients at this clinic are smokers, and then this is 80%. Okay, so now we want to calculate what is the probability that a patient at this clinic has respiratory problems, right? So we want to calculate the probability of this and that, right? The two destinations. Okay, again, you know that you have to multiply the probability on the edge. So for this destination, the probability is 0.2 times 0.7. For the other destination, is 0.8 times 1/4, right? So altogether is this. So the tree is indeed helpful. Now finally, so that's the game, right? So the game, for those who came in late and happens that you never heard of this, it's a fun game. So so the game was, okay, we said there's a Ferrari here and two goats, right? So you choose one, and then the host will open the one which is not Ferrari, okay, and ask you whether you want to switch, right? Okay, so we want to decide using probability to make a decision so that we have better chance to get the Ferrari, okay? Okay, so here this picture says, explain this, right? So the car can be hidden inside door 1, right? And this is the car hidden inside door 2. This is the car hidden behind door 3. So 1/3, 1/3, 1/3. The chance is 1/3, right? Now let's assume you pick. Let's assume the reference point, which is the door you pick, is number 1. It doesn't matter, right? So the same argument holds. So let's assume you pick. Okay, in any situation, the reference point is you pick number 1. Okay, so let's look at each scenario. So suppose the car is really there. Okay. Now, then the host will, because he can open either doors. The rule says he must open the one with, if it's only one, then he has no choice. But if the two doors are always goals, then he randomly pick one, right? So he has two possibilities. So he randomly opens either the gold door. So for example, he opened the second one, and then you swap, then you lose, right? So but what is the chance of this happening? Just now we learned the trees, right? So it's like 1/3 to get into this situation. To get this square, we get half chance, right? Because the host will open either, so it is half and half. So the probability we are here is 1/6, right? So this is okay, right? You are with me. Now, by the same reason, the probability of the arriving here again is 1/6, because there's 1/3 of chance here, and then here is another 1/2, so it's 1/6. Okay. So this is the analysis of the first possibility, right? Now, in this possibility, suppose the car is hidden behind door 2. Suppose it's here. Now, this actually is the crucial part of the game. So the host, in this case, he has no choice. So he must open this door because he cannot open to show the car. So he has no choice. So this is with probability 1, we are here. Okay? So now suppose you switch, and then you win, right? Because if you switch, you win. In these two situations, when you switch, you lose. In this situation, if you switch, you lose. So what is the probability? We have 1/3 of chance getting in the middle, but here this is 100% because the host has no choice. He has to open. So the probability of this happening is 1/3. Okay. By the same reason, right? So I guess you can see these are symmetric. Again, the host has no choice. He has to open the door too. And then if you swap, if you switch, you win. So switch win, the probability is 1/3, 1/3. So we have, suppose you switch, you have 2/3 of chance of winning, right? If you do not switch, you lose, but the chance is 1/3. So switching will give you better chance, right? So you should switch, right? If you use a tree form, you can, this is a tree form of saying the same thing. So you have 1/3, 1/3, the Ferrari is 1/3, 1/3, 1/3 behind these doors. And this is what happened in the first gate. This is the same thing, right? And then this is what happened if it's there, it's there. So the answer for this is, I repeat, right? So the probability of winning if you switch is 2/3. So in other words, you should switch. Okay. And there are follow-ups of these saying, suppose the host randomly, so he doesn't care whether the door, he doesn't know where the car is. So after you choose, he just pick one. So in this case, whether the switching will give you any advantage, right? For those who are very good at statistics, or you can answer those questions. I think I'll stop here. So today I stopped a little bit early because the next topic will be about expectations and so on and so forth. So probably we need some time to digest this. Suppose this is the first time you have seen these concepts. By the way, who has that piece of paper? Do you find this thing? You didn't see it. Really hard to see. So there are at least two persons born at September 12. Good. So okay. So it is correct, right? In this case, so we do have at least two persons. So anyway, so see you on Friday. Also, the midterm is coming, so I want to repeat. Okay, some of you send me emails, but I would like to answer things in at least I'll repeat my answer to everyone. So the question they ask is whether the format of the midterm is similar to the sample I upload on IVLE. The answer is yes. It will be multiple choice or true or false questions. But the number of questions may not be 20. And the topics certainly are different. So because we change the sequence of the syllabus in the topics. And also people ask, right, so what topic I'm going to cover? So I'm going to cover up to counting, including counting. The reason is at week 6, we are barely able to finish tutorial 4. So that is about counting. So I will cover until counting. And what else? Oh, some people ask me whether the help sheet can be printed. Well, the purpose of help sheet is help you to summarize and also avoid too many memorize. But if you really want to print, okay, I don't care. So you can print, but it probably reduce the anyway. So I don't care. So you can bring the, but you can only have one A4 size, one piece of paper. Okay. Anything else you want to ask? Okay, so you can email me, and then I will answer again this Friday and in public. And people watching webcast, you can also email me. Okay.